All right, we got Newton's first law. Keep it in mind. Things keep on going forever if the net force is zero. That is, if the forces are balanced. It's the law of equilibrium, not inertia. We got Newton's second law, which really encompasses it all, and that's going to be the method. That's what we're going to go to. But there's an intuition we need in our analysis. Because, again, as I mentioned before, objects are interacting. That's what the force is. And this idea of interaction is going to go deep. We talk about momentum and energy as well. But for now, forces, by definition, a force is an interaction. There's two objects interacting, pushing and pulling on each other. Okay? And so we're going to talk about Newton's third law here in a second and get that straight. When we see two objects interacting, red on blue, again, we have to choose in our analysis. Are we just interested in blue? Are we interested in the whole system? So red and blue can be our receiver, our system. Or maybe we're just interested in red, or maybe in the analysis we need to deal with blue, and then we need to deal with red. Or maybe we need to deal with blue separately, and then the whole system. We're going to see that quite a bit. Okay, so let's do Newton's third law correctly. You can get an intuition for this. But there are some surprises. Our brain goes one place and we get tricked, so let's not do this. Forces are interactions. Often Newton's third law is stated as equal and opposite forces. I recommend abolishing that language. I'll show you why it leads to problems. Often it's said action and reaction. Not so bad, but it's a little bit, let's just say it for what it is, okay? Because when you get these snappy little phrases, maybe they're helpful if they're insightful enough, but people misinterpret that a lot. Here is what it is, straight up. So just do this. If you can do this, if you write it down, if you've got a problem that you're looking at, and you say, okay, I've got a force, which is an interaction, a push or pull, from object B on object A, then that will be equal in strength, but opposite in direction to the force vector, interaction, push or pull, from A on B. The force from B on A is equal in strength but opposite in direction the force from A on B. That is it. And so if you're trying to analyze something, fill in the blanks with the name, whatever B is. Maybe B is a bus and A is an apple. I don't know, whatever. A is an apple. And then think about what it means. Be very careful. There are times when this might serve, but more often than not, this leads to confusion. And that is, if you write this as an equality, so this is correct, but again, the confusion with what equals means, I'm going to give you another color here. If you write force, that color, force, and let's write the vector. And eventually you get tired of writing from on. I suggest writing that for quite a while until you get tired of it, then write it more, and then you drill it in. But we do a notation. Now some people here would put the B first and the A next, or that some people flip it. So you have to look at your paper or your text and see how they're using this. But I'll do from B, and we could even just help ourselves with B on A. That works pretty well. Force B on A equals force A on B. Now that's wrong. Why is that wrong? Well, two ways you can do this. You can put absolute value signs, the magnitude, and then that's fine, that's this part. Or you can encode this part with, obviously, a negative sign. However, I'm going to recommend not writing that. If you see it, translate that meaning to this. And there's a reason, and the reason is when you do your analysis, you're going to look at Newton's second law either for B, or for A, in this case, on A, if A is our receiver. You're going to do Newton's second law, and you don't care what happens to B. And then that goes in there. This doesn't go in. If you're looking at A, I don't care what happens to you. And maybe if you need to, then you'll look at B. And then you look at what all the forces on B. And you don't care what happened to the sources. Now B is the receiver. I don't care what happens to the sources. I care about the receiver. The receiver can be B, and maybe I'll go, okay, now I need to look at A. What are all the forces on A? I don't care what happens to sources. That's the source of confusion. Let's build this intuition here in just a second. Okay, so you can get this multiple ways. But if you have to trust this, because your intuition is going to get played with here, right? You're driving down the road. A bug hits your windshield, right? So a bug hits your windshield. And who gets hit harder? The bug or the car? If you're clear, don't answer. Who gets hit harder? What do you think people often say? Who looks like it got hit harder? The bug, right? The bug, it got squashed. The bug, but here's the key. First, whether you believe it or not, you use this as your answer key. Not this guy, this guy. So any interaction, if you get a car, maybe it's an Audi, got hit by the bug, then the bug got hit by the Audi with exactly the same strength, equal strength, opposite direction. Exactly the same. The key is, who got affected more? The bug, because the bug has less mass. We go back to Newton's second law. If you have less mass, you'll get more acceleration from the same force. So we get confused by the effect. The effect is that I hit the ball. Who got hit more, the ball or me? I got the same strength, opposite direction. I hit it that way, it hit me this way. Who got affected more? The ball. It's got less mass. Also, I've got other forces on me. I got the force of the ground pushing up and gravity and friction and things like that. So you just have to look at, when we analyze it, decide, I care about A, or I care about B. I care about my car. I don't care about my bug. I don't care what happened to the bug. Or I care about the bug. I don't care about my car. So whatever it is. But it's still true. Watch, this is easy. Here, one way to do this. Push on something. Push on your tabletop, right? Let's do that. Push on my tabletop. Here's my tabletop. Pushing. I push lightly. Relax your hand. I'm pushing which direction? The force on the table is down from my fingers, right? The force on my fingers is up because I can't, well, maybe I can, I don't know. That pushes it up. Notice, if I increase the strength, if I push down harder, the tabletop pushes up harder. So we think of action as I take action to create the force and this reacts by pushing back. That's the thinking, but be careful with that. Just use this, okay? Because inanimate objects can collide. You know, a comet can come and hit Earth, and no one's like willing it to happen as far as this. I don't know. So there, if you push harder, so I push into the board, it pushes back. Same strength. I push harder, it pushes harder. Don't believe it? Slap your table. Slap softly, it slaps back softly. Slap hard, ow. If you really don't believe it, you've got to get this in your head, so do whatever it takes. So slap your cheek and then go like that. And this is the beautiful thing. So, you know, you're in your argument with your significant other and they slap you. And you go, I hit you as hard as you hit me. But the effect could be very different, right? You could have a bloody nose and they just have a red hand or whatever. But still, it still works, right? Prize fighter, you lose the prize fight. I hit them as hard as they hit me every time. In my nose, but my chin. So, but this is true. The effect, and this is a deep understanding. The effect, what happens, depends on the mass and the strength and direction of the forces, the interaction. Force is an interaction. MA is not a force. It's the mass of the object, the inertia, the gravitational property, times the acceleration, the description of its change, is not a force. The forces cause that acceleration. The mass resists the acceleration. And that's it. So then when we do our analysis, we just have to clearly decide, do I care about A? And sure, B is affecting A, but I don't care what happens to B. Right? You slap someone, you don't care what happens to your hand, I guess. I don't know, whatever. So watch this. Walk. Now walking all of a sudden becomes weird. Right? Wow. How did I do that? Did I accelerate? I accelerated, right? In fact, I accelerated twice. I increased my speed, and I decreased my speed. I can't do that on my own. I can't do it on my own, right? I mean, I just float in space, right, or stay at rest. So something had to push me. So who pushed me? The ground, right? You try doing it on slick ice and you're not going to get very far. You can push on the ice, it's not going to push back. You need a little roughness, a little traction, right? So if I push on the ground backwards, the ground will push on me forward. Now I'm moving, here's the slow motion. And then I stop. I push on the ground forward, step on a slippery thing, and you'll keep going, and it pushes back. Now I increase speed, and I decrease speed, and I increase speed, and I decrease speed, and I increase speed, and then, so just walk down the hall like this till you get it. Right? And then you got it. So there's an interaction. What happens to you? I can speed up by pushing off. Right? It might not move because it's held into place. I can push off. Right? So I get a force by pushing on other things. In space, you push out gas, jets of gas. If I push the gas this way, it pushes me that way. If I push it, I can rotate. I can shoot out gas this way, and if I shoot out gas that way, I'm pushing it that way, and it'll go like that. And that's how you operate in space. You can't just float and just go, turn, please turn. You're just going to float. Now, as a whole body, you can turn, you can rotate as a body. And so this is the last little introductory piece, and that is, Alejandra, when we're doing this analysis initially, we're talking about objects as though they are, we call them point particles, which really means negligible size, or at least we're ignoring it. Negligible size, negligible shape, just a point. Really, of course, you know, what is that? And we'll talk about subatomic particles another day. But so we treat this as just an object and not worrying about rotations till another chapter. We're building a framework where we can. So this object is a projectile and it's rotating. It's two motions. And so we're going to build up these descriptions, and it's really cool. All right, so, you know, what is an object? Well, there's the object here and the string. We might call it a mass, but it's not a mass. That mass isn't a thing. It's a property that has, it's a thing with various properties. Anyway, there's the string. Is it the whole thing? You know, what is it? Is my object the entire unit, including the spring, or is it just this, or is it just this? That's going to be part of our analysis. So there's that. Now I want to do one more thing on Newton's third law and show you why this is so important. A common mistake. Here we go. Right? Now I have to choose what I'm looking at. More than likely, I look at this hooked object, which we call a hooked mass because it's made for its mass properties, but nonetheless it's a hooked object. Okay, so I could look at it, look at the forces on it, once from touching. I'm not touching it, so this is critical. I am not touching that hooked object. I'm affecting it, but we have to break it down. You really have to be picky. The forces on that hooked object come from the touching things touching it, the board, and then the weird action at a distance, non-contact interactions of, say, gravity, magnetism, electric, strong, weak. So gravity pulling down is a type of force. What's the object? Earth is pulling with a force of gravity downward. The board is pushing upward with what's called a normal force. We'll get into that in a bit. Okay. In this case, what's the net force equal to? Because you can see that it's not accelerating, right? If acceleration is 0, the net force has to be 0. There could be a million forces still. Net force is 0. I don't know, if you want to look at the individual ones, you've got to put them in. Okay, so the net force is 0. Now, the force of gravity is down, represented by my green vector here. And the normal force is up, and they're equal in strength, because they're the only forces, so the only way they can balance is to be equal in strength, opposite direction. I have a force of gravity from Earth. Get this. This is a common mistake. The force, the normal force from the surface on the mass, on the Hook, Mr. Hook, whatever, Captain Hook. The force up from the surface, the force down from Earth, force of gravity. The net force is 0, they balance. So those forces are equal in strength and opposite in direction. Is that Newton's third law? There's my situation. I'm going to do what's called a free body diagram. I'm going to go, okay, well, I've got a force downward, excuse my color change, force of gravity downward from Earth, and I've got a force upward, a normal force, force normal. These are equal in strength, opposite in direction. You can see that because the acceleration is 0. And this is not Newton's third law. This is not Newton's third law. It doesn't fit in here because this guy, if I'm more careful, if I'm really careful, I'll avoid mistakes and train my thinking. So at this point, as clumsy as it is, it's the force normal from, say, table or surface. I'll just say surface. Surface on, I'll say block. That's from the surface on the block. And this guy here is the force gravity from all parts of Earth on the block. And the key here is that both of these forces are on the block. And so what would Newton's third law be here? If you use that formula and go slow and careful, being wary, you can get it. And if you get this, you pretty much are going to be there. The Newton's third law is equal strength, but opposite direction to the force from the block on the surface. And I guess I should throw vectors in there. And then here, this would be equal and opposite vectors of force from, again, the block now on all of Earth, which isn't going to have much effect. That's Newton's third law. If you flip it, force from Earth on block, force from block on Earth, that's Newton's third law. These are equal and opposite, but they're both on the block. If I'm analyzing the block, I don't care what happens to the Earth, and I don't care what happens to the surface. I care what happens on the block. That is not Newton's third law. What happens back in the interaction is Newton's third law. It's the interaction that matters. And so that's tricky, but you got it. You're masters. Cool. All right, let's do a method.